Hey, John here. Thanks to every one of my patrons. Can't say enough. Thank you, thank you, thank you. Last night I had just enough time to eke this thing together, slap together a quick drawing. Let's have a look-see at the upgrades I've made since the last time we looked at this video interface here, okay? So nothing changed from where we left off. All I did is add to it, okay? So here's the decoder. I talked about that last time. We've got the reading and the writing, and A0 is used to pick which port we want to talk to. Data lines go back to the Z80. And now what have I done? I've added the dynamic RAM interface over here. Where are the DRAMs? Okay. Now, these DRAMs are, it's not clear whether I want to have the backwards numbering that TI loves to do on the address bus or not. This would probably matter if it was any other DRAM chip, and or if it used like a burst page mode data transfer. We can see from the data sheet for the DRAMs here that the address is sent to the DRAMs, right? The 8 bits for the row number goes out on A0 through 7, and then 6 more bits that select the column address go out on 1 through 6. If you don't really know what this means, the point is that you've got a 16K address, or 16K number of bytes in the chip, and you need to express that using 14 bits. So that's 8 plus 6, all right? And you'll notice that the 6 bits that go out on A1 through 6, so A0 is not used during this phase, and A7 is not used, right? So you send half the address out, and then a little bit later you send the other half of the address out, rounding off, right? So the 8 bits go out, then the 6 bits. My whole point here is that the 6 bits go out centered in the 8. You ignore the low and the high. Therefore, if it's wired in backwards, it will still work, because the low and high bits are ignored, which makes it symmetric. So therefore, if the low bit is on A0 or A7 and the high bit's on A7 or A0, those two are ignored anyway. My point is you'll be counting up or down, and the chip doesn't really care, provided that we're basically addressing 1 byte at a time. You know, the RAM doesn't really care whether you store the bytes in one location versus another. Now, I had to create this footprint myself. This is, I guess, old enough that it's not in the KiCad standard default library that you get. At least this is version 5. I'm still stuck on version 5 because of the OS release that I'm running, and Wayland, and the inability to record. Blah, 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 blah. No, sorry, I can't upgrade yet because nothing works on my distribution. It's not KiCad, it's everything else. So one more project in version 5 here. Anyway, bottom line is the data sheet that I used when I created this footprint also comes from Texas Instruments, and I numbered these pins the way Texas Instruments did. So I suspect this is the right way to do this. We'll find out when I order a board, right? And you then hook up the read-write pins as you would normally do it. The G pin is the output enable pin, and this is just permanently tied on. Well, the fun and games with the G pin are described in here, so we don't really care except when we're trying to write into the chip, right? We don't want it sending us data when we're trying to send the chip data. So it says right in here that, you're reading or writing depending on the write input, okay? High on write means I want to read out of the chip, and all is well. Then it says that the data input is disabled when the read mode is selected, all right? So that means it won't ingest any data. When W goes low, prior to CAS, which has to do with how the address data gets sent into the chip, and the video chip, the VDP generates the CAS and all that stuff in the right way, okay? It says data out will remain in the high impedance state. In other words, it's off, which will allow a write cycle to take place even though G is grounded. Okay, so what all this really boils down to is if the VDP uses what we call early write mode when it's trying to send stuff into the DRAM, then it'll work fine, even though I tie the G-bar pin low. And to that end, if we go back to the 9118 manual, you'll notice it uses the early write cycle. So this is exactly what we want, all right? You want to dig through all this. What that boils down to is that the VDP asserts the write signal here before CAS goes low here. And this all has to do with, how does all those bits get sent into the DRAM when you've only got an 8-bit bus? They're multiplexed. Spoiler alert, right? So you send 8 bits for the row number here, and then you lower RAS to let it know the row is ready, and then you change the address to the column, the 6 column bits in the center, 6 bits of the 8-bit bus, then you lower CAS here, okay? And early write simply means that I assert write before I assert CAS, so the chip knows I'm really writing even though the G pin says I want to read. Okay, so that's what all that means. It's designed to be used this way. Best I can tell, this is what we want to do. What else is going on over here? We'll come back and look at that in a minute. This is the interface to the Z80. You've seen this before. This is the retro board connector. One thing new I added over here is this interrupt. And I don't know whether this is going to be so this is a little troublesome here, okay? The interrupt output pin, what this is really used for, is what's useful for, in my case, I want to be able to know when a screen has been updated. Every time there's honestly, I don't know if it updates every field, because remember, composite video is what we call interlaced. It runs at 60 hertz, but only draws half the image each time it draws a screen. So it's one field, we say, 60 times a second. 2 fields in composite video constitutes a frame. So this will either generate an interrupt per field or an interrupt per frame. I haven't read all the manual yet. One way or another, we'll turn on these interrupts and we'll be able to synchronize our code that will run on the retro board such that we can draw one new image, if we want to, for each frame or each field. And we know when that is because this will generate an interrupt, okay? Now, what's the weird thing about this is that this is you got a totem pole driver on it, according to the manual. I believe that's true. And we need an open collector. So we can put a diode in here that says if the interrupt is ever low, let it propagate through and pull down the interrupt line. If the interrupt is ever high, this diode will block it so that it doesn't pull up the interrupt line if something else is driving it low. Now, I also put a jumper in here because we may not want this connected in any way, shape, or form. And that may happen if we can't really get the software to work right. Now, I haven't done a lot of interrupt tinkering yet with the Z80 Retro, but the I/O ports and stuff that are on the retro board itself, the CTC, in the SIO, are configured to run in what we call mode 2. And this thing doesn't know how to speak Z80 interrupts. So if I connect this up directly to the interrupt bus, we're only going to be able to generate mode 0 interrupts. We'll talk more about that later when we start messing with the code. But looking ahead a little bit, if we can't get that to work, it's not going to. Point is, you can't have mode 0 interrupts coming from one device and mode 2 from. This is a galactic setting. It's a one and done type of thing you do on your Z80. You either say everybody generates an interrupt and I don't care who it is and I have one handler for everything, and then you get to play needle in a haystack to figure out what happened, or you use something like a different mode where there's a handshake and a dialogue that takes place between the Z80 and the peripheral device that this thing is unable to do. And that's their problem. And the device can then say, hey, I'm the one doing it, and will you please call my subroutine instead of the other ones? And then the Z80 can, what we call it, use a vectored interrupt. Okay. In other words, it vectors directly to the handler for this chip. So you don't have to play the, is this the why I'm here? Is that why I'm there? And so on in your interrupt handler, which is, as anyone would know, who's actually had to suffer through all this before, is a waste of time. It creates a lot of latency in your interrupt handlers. Okay. So this is a little bit annoying, and I didn't do us a lot of favors when I did the retro, in that there's no extra pins on the header that comes out over here that allows us to do things like, well, maybe I can send the interrupt output from the video chip over to the CTC or the SIO, for that matter, that could, on behalf of something like the 9118, generate an interrupt in a sane and useful way, and that could coexist with everything else. So sorry about that. Bit of an oversight. Well, yes and no on the oversight. It's just, that's what we got to work with. This doesn't want to generate compatible interrupts. I mean, I could put a PIO on this board here and then use that to do it or something like that. I mean, these are all options, all right? But my goal right now is to get through a prototype board and get video coming out of the retro board. All right. Now, this is here as a maybe option. We'll figure it out later. Now, we also played around a little bit with the video. We talked about this before, and this is a super duper kitchen sink situation here. All right. I looked around the web. I saw other people using this and similar chips, and I saw everyone seems to copy the Steve Ciarcia article design. And at least one of them said theirs did not work and they couldn't figure out why. And I saw a video flipping up the screen which suggested their sync wasn't working. Now, I believe I know what's wrong with that one. I sent a note to the designer. We'll see if they respond back. This is why I think that one doesn't work. So, as we talked about before, when ComVid, this is the signal, remember, that comes out of the 9118. This is the composite video right out of this chip. Now, if you look at the manual for the 9118 and the 9918, okay, the difference between the 9918 and the 9118 is the way the memory is hooked up. We'd have to have 8 memory chips versus 2. All right, there doc says the only real difference is this. Everything else is the same, okay? Now, according to this, you're supposed to pull this down with a 470 ohm resistor. And then you've got composite video coming out over here. Now, to me, this doesn't make any sense at all, because composite video, to me, means you're going to go into something that's got a 75 ohm terminator on the far side. So what's the point of this? It'll lower the impedance even more. And you then look around in the rest of the data sheets. This here being the data sheet for the 9118, or the little bit of it that I can find online that someone posted. And it says that the external load resistor on ComVid or any of the other outputs for the other chips, the minimum resistance value is 470. Suggesting that when I just shoved it in my video capture device and when I was playing around with it before is not what we're supposed to be doing here. We're overloading the output of the chip. So what to do? Well, I decided to do this. These are like 4 different designs, the union of 4 different designs, all in one laid out thing. And we can either populate or not populate various parts or short them out and stuff like that, and play around with some games here. I did some of this with my breadboard, and I could see various differences, but the noise was enormous, and breadboards are noisy, and I'm like, let's just make a board and see what happens, all right? So I just threw everything on here. Here's what we're going to do. If you don't populate R7, and you short R1, and you don't provide these capacitors over here, or even if you do, it wouldn't make any difference in that scenario, right? Short R1, open R7. These resistances here are the same values that you see in the Steve Ciarcia article. If I put this resistor in my design, the noise that comes out over here goes way up. So I don't even know what this is for. What we've got is Q3 is an emitter follower. Any voltage that is here is reflected over here minus the junction drop. Okay? So I'm not sure why this is here. Anybody? Please throw something in the notes. I'm going to design it into the board so I can put it in if I want. We can try it. Don't like it, remove it, whatever we want. Okay? If you don't have R7 in here, whether you've got a 10K in here or not, there's almost no load on ComVid. So what happens is, and I showed this before, if you don't put any load on there, or a high impedance load, which is what this circuit represents, if you don't have something in R7 here, then what happens is the voltage is way too high on ComVid, and the sync is all off, which is why I think that the design I saw floating around on YouTube, somebody did it about a year ago, said their video didn't look right. No, I don't believe they had a video, a oscilloscope capture showing what I showed the other day. I'd like to see that on their case, because I don't think this is going to work right at all. Now, maybe the size on this resistor was wrong. I don't know. I mean, you could put a small resistor in here if you put in maybe this was 100 ohms instead, right? Because that's closer to 470 as it goes through here. But that's not really an emitter follower. I'm not sure what this is. I don't know. I don't know what R2 is for. Okay, I don't really know. So I'm going to stick in a 470 to ground. Now, in a way, this is sort of the same sort of thing, right? You got your something that's going to ground over here. But as the voltage here goes up, this gets pulled up. So this really isn't going to ground, because as this thing raises the voltage on the emitter, then this coming back here, I don't know what that's for. All right. Anybody that lives in the analog world, tell me about this thing over here. I'm a digital guy. This is about as far as I go with analog stuff. All right. So what I'm thinking is, don't put in R2, pull this thing down with a 470, because that's what the spec sheet says. And I also tested this on a breadboard, by the way. And it turns out that these resistances over here are a voltage divider, because the voltage is actually too high. Because NTSC says that the maximum voltage when the signal's white should be 0.7 volts over the voltage when it's black. And that's like 0.3 over the sync tip ground and so on. You can Google NTSC video and take a look and see what that's all about. But if you divide this way, you end up with the right amplitude coming out over here. Okay? Now, if you don't divide it, it'll probably still work, because most NTSC inputs have an automatic gain control, and it'll attenuate it automatically. But if you do that, you might lose dynamic range, or the color will get all messed up and stuff like that. The color will probably be wrong anyway. I was unable to get a really good consistent color coming out of my chip. And, the funny thing is that people in the business say that NTSC stands for never the same color. Because getting the color to come out right with composite video has forever been a problem. All right. So, surprise, our color will probably look wonky. And if you look in the design in the TI document and the Steve CRC article, he puts a small variable capacitor in here to tweak this frequency of this crystal a little bit, which could cause the color tint to change a little bit as it comes out of the circuit. Okay. I'm going to just leave mine out of whack and say what comes out of here is what I'm going to get. All right. And we'll see what happens when we're on a circuit board, because on a breadboard, there's so many parasitics and crazy reflections and stuff. I have no idea if it'll even look close to what I got on the breadboard by the time the smoke clears. All right. So far, so good. I'm going to terminate this to get the right signal that we saw on the scope before. I'm going to remove this because I don't know what it's doing anyway, and mine looks better without it. In the end, who cares? If it looks right and the voltages are right, that's what you do, right? Up here, what's this all about? Well, this seemed like a good idea when I did it originally. I've seen some people playing games over here. Why do we have this going on? Well, I think that this will do nothing whatsoever. Okay, but the idea and the intent, and I believe in the circuit where I saw someone did this, was that if you have a low, you need a fairly low resistance here. The idea is that if you put some filter caps over here and they charge up through this resistance, and something over here draws a lot of current, it won't drain these capacitors back out. So having something like 10 or 50 ohms or even 100 ohms over here, 100 would actually be way too much because this whole thing, remember, needs to be able to supply the high voltage. It has to go up to 1 volt or maybe 2 volts over here before it's divided out 1.5 volts or something like that, and be terminated into these low resistances over here in the 75 over there. So this can't be too big. Otherwise, this voltage will never get up high enough. In other words, the bigger one you put here, the more you got to tinker around with these over there, and it may not work. So you could either put a small resistance like this in here, or you could put a ferrite bead in here, or you could put an inductor in here, or something like that. All right. So this is just here to try and filter the voltage, the DC voltage here, to make sure it's as stable as possible. Okay, that's great. Do I think it's worth doing? I suspect not. And the reason is this. If I have 5 volts, I think I'm going to just shunt R1. We could put some caps in here, but I don't think this is going to do us any good. Because if we have 5 volts in here and it's super noisy, all right? If this thing is so noisy that the voltage ever drops all the way down below 2 volts, which is how low it would have to be in order to cause a problem over here. Because remember, the most voltage that ever comes out over here is about 1 volt, 1.5 volts. Okay, so as long as this thing's at 2 volts or greater, this circuit will work fine. But if it ever goes down that low, everything else will crash. Therefore, I'm pretty sure this will never droop down, even if it's noisy and crazy. All right, and if it never goes low enough to cause this to clip, then this transistor could care less. It wouldn't pass it anyway. So I don't expect to see that coming through here. Now, you could say this could be, digital logic switching noise and many, many megahertz. Yeah, there could be some weird noise effects coming through here. That's why I put it in here. I have no faith in it working or doing anything useful, but I pinned it all out, okay? So please, comments below. What do we do with these parts? I think I got enough footprints to do a couple of different options. Certainly in version 0 of this board design, I got enough options. That's all I'm saying. And we just populate or don't populate or put a shunt in here or a bigger or whatever size parts in there, okay? That's what's going on with this thing. And I'm pretty sure that R2 is going to be a no-go. What's all this other stuff going on over here? Well, I, as you saw in the beginning of the video, found an old joystick. It's an Atari-style joystick. If I'm going to have video, even if it's noisy video, which is actually going to be really true to period, if you think about it, this thing, even with the noise coming off the breadboard and all that, looked perfect to me. Back in the day, I'd plug up VIC-20 into a TV set, herringbone, image noise everywhere. It looked terrible. And you'd put 2 colors next to them and bleed all over the place. It was nasty. And this will probably start doing that too, because so far all I can get is a solid color, which is always going to be the best possible scenario. Once we start putting dots and stuff up there next to other colored dots, this will fall apart probably as well. But it'll probably still look better than anything I've ever seen before on composite video, all right? Because I will also add, everything that I used back in the day was RF. So once you got composite and you go through an RF modulator and watch it on channel 2, it's even worse. So this is going to look wonderful to those of us in the late 70s and 1980, 81, who was looking at a VIC-20 or a Commodore 64 on your home TV. Now, this is going to be beautiful. Even if it's horrible, it's better than that. Okay. Okay, so And that's, again, because it will be used in this scenario without an RF modulator. We'll just plug it in, a composite input on either a video recorder, which is what I've been using so far, a video capture device, or my TV in the living room upstairs. That in the U.S., we still have composite inputs on most TVs. I don't know if that's still law or not, but it has been for a long time. The FCC said you want to sell something here, you have to have, it has to be able to tune in every channel in the U.S., and it has to have compatible inputs for backwards compatibility. That's so that consumers have an old VCR, you can still hook it up, blah, 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 blah. But honestly, I'm not sure that's still by law or what, but my Sony Bravia still has composite. I'm just saying. Okay, so therefore, what's going on with all this? Okay, I found some old joysticks lying around that are Atari compatible, which means they have a DB9 connector on them. And if you're young, you might think of the DB9 as a COM port or an old COM port, like on your PC, or the RS-232 ports on the Retro board with the ribbon cable that I made that has a DB9 on it for like RS-232, right? Well, the Atari joysticks use the same connector. So what I did is I noticed when I threw my board together, there was a little extra real estate, so I shoehorned in a pair of DB9s. And I shoehorned in a pair of these LS244s. We've seen these before as my input, general purpose input bits on the Z80 Retro board. Now, I also have some more pull-ups. I just pinned them out using the same footprint as the parts that are on the Retro board. I guess I should put values on these. Anything 1K to 10K will probably work fine. So I'm going to just use extra ones that I have left over from my Retro board for this. This is the same chip that's on the Retro board as well. So if you bought some spares, you already have these, the 138, or you can use the HCT 130. Any 138s will do for this, I'm sure. As well. All right. Now, what's this other 138 here? So I added these two chips and the 138 here. So what happens is, remember this decoder, I talked about it last time. These output values here, 0 through 3 are not viable for my purposes. Right? Yes, I know we could play some games if we wanted to. Don't need to. Outputs 4, 5, and 6, and by this reference that we don't want to use these is because these will go active in port numbers that are less than 80 in hex, and those are used to some degree on the Retro board. So I'm going to air quote and say those are reserved. These will go active on 80 and A0 and B0 and stuff like that. Okay, so these two pins here I mark as going valid at port 80 and 81. And this one down here will go valid, if we follow this up here, when I'm addressing values between A0 and through BF. Okay, these things go through 80 through 9F in that range. We don't need them all, but in order to decode more pins to reduce the number of addresses that it enables it with, we'd have to play some more games. I just wasted them to simplify the design, okay? Now, this pin here, my point is it will go low when I'm accessing ports that start with A0, A1, A2, A3, and so on up to BF, and I'm reading. I explained all this before. If read is low, then this pin will go active, which is low. When A5 and A7 are what? A7 would be a 1, and A6 would have to be a 0 because it's hooked up over here, and A5 would have to be a 1. Yes. Okay? That's when this will go true, and that represents the addresses that start from A0 and end at BF, as I've said repeatedly already. So if we then decode the rest of the address lines, and we say A4 must always be low, A3 must always be high. Why did I do that? Yeah, because these are unused enable pins, and I didn't want to waste more port numbers than I really had to. And then I got A2, A1, and A0 hooked down to here. So these are fully decoded. All 8 address lines are decoded here. So in this situation, and mostly because this A3 has to be high, right? So we don't actually have one that says A0 here, right? Do a truth table, you'll see what's going on. Pretty sure I'm right here. This one will go low when I'm reading from port A8. This will go low on A9 and AA, AB, and so on. I don't need these. I'm only using two. Those two pins come over here and enable the 244. When this is enabled, the data over here on the inputs, which is pulled up here, and we'll see are connected to the DB9, so we can read the joystick, flow through here to the data lines here, D0 through D7, which is the same data lines that run over here to the retro board. Okay, so these are just two more 8-bit input ports. We don't even use all the bits because these only generate, I don't know, like 6 data bits, of which only 5 are used on the joystick that I have, because these are designed to be able to support 2 separate push buttons, and mine only has 1. Okay, I also hooked up the all the I/O general purpose input bits on those not latches that go through these 244s up here. Okay, I just stuck a header in here so we can just tie them in and play around, and I put some power and ground on there so that when you're probing around, you can short these out and get very upset. This may not be the best way to wire this up. I'm just saying. But I'm going to go ahead and do this. Again, this is just being slapped together so we can do some testing on something that's not, a mess of wires all over the place, generating so much noise. And in the last video, you saw the ringing on those signals were like 2 volts peak. So bad. It was unbelievable. So let's get this thing cleaned up and see what it'll do, all right? Got a couple of bypass caps. This is where I drew in my 470 that I use with this 470 that I straddled across my 9118 on the breadboard. The signal output improved massively, so I'm keeping that in the design, all right? So that's the schematic. And this is the circuit board that I've routed. Now, I started by copying the project that has the Flash programmer on it, and then I deleted everything off the Flash programmer except for the mounting holes and the outline and the location of this connector over here, because we know this lines up with the retro board. And it has a weird, wonky alignment because I foolishly forgot to lock it down, and it moved a little bit, so it's sort of like some really weird dimension in here. It's not impossible, but it's not perfect. It's real easy to figure it out. I think I went over it when I was talking about how to build the Flash programmer board in the first place, and how I calculated it relative to this hole or something like that. But it was easier to just copy the other one, leave it alone, lock it in the design this time, and just replace all the parts and throw on some tracks. Okay, so what went awry here? Well, this thing came out okay until I decided that I wanted to add these extra I/O ports over here. So I suspect we're going to be all right. And I say that because my retro board works with a morass of wires that are like 9 miles long with that breadboard and everything. And granted, the ringing is so bad that I'm shocked it works at all, as you saw on the scope last time. So this is probably better than that. But, I mean, I'm not really thrilled because I bring in the data and stuff on this connector from the retro. The data lines run over here. Actually, the data lines are mostly these red lines, I think, here, and there's some of them over here. And they come in here, and they hook up to the TI chip here. Most of the data lines, I think, hook up around down there. Yeah, you can see D7 and so on going around here. And then these red lines run underneath the RAM over to here, up there, and then connect up to the 2 buffers here, the tri-state buffers that we use to take a peek at the joystick inputs over here. Okay, so the data lines on here, from the retro board are coming over around and up and around here. That's kind of 4 inches, 5 inches of tracks here, and on the retro board they also kind of wind around a lot. Not really happy with all that. I'm very confident that this will work and it will be reliable and fun, so I'm pretty sure it's okay. But maybe I should have put a buffer in here or something to kind of not load down the Z80 so much and not have these giant antennas all over the place that are directly wired into the Z80 board. But, you know, I've done far worse and got away with it. I think with 5-volt systems running at 10 megahertz, this is okay. And by the way, I went with 4 layers on here. It may not need 4 layers, but with 4 layers, you've got a giant ground plane in here. If I turn on all the layers, inside here, there's not going to be a lot of loop currents or anything. And yes, I know the inner layers are going to be, like 5 volts in ground. So as we go between the top and the bottom, I don't have stitching vias. Maybe I should put some. I don't know. Maybe I'll tweak some into the design before I order the boards. It'll work without them. It may be less noisy and more robust with them. I'm just saying. Maybe. Yeah, because when you bump up like this, go over and then go back onto the back of the board, these kind of jumps, this one here and these here, I might want to put some, as I like to say when I had other people routing my boards, throw some bullet holes in over here, okay, to help that situation out a little bit. But I'm pretty sure this board will go. Might be noisy. I'll probably have a flaw in here, but like I said, I'd like to just see what happens when we run the board without, 6-inch long jumper wires on my breadboard and see what happens. All right. So in the middle of the board here, these are where all the resistors are that do the dividers and the filter. And this is your emitter follower from this would be the ComVid signal right there. Okay. This is the oscillator and its load caps. I would never do this if I didn't have a ground and a power plane underneath all this, plus another ground on the top of the board. If we look at the layers here, red is the component side. And if we turn off the front side copper, you're now looking at a power plane, and you turn that one off, we're now looking at another ground plane before you get all the way to the back layer where there's some signal over here. I'm pretty happy with this being isolated enough from this. This is going to be a nasty bunch of noise over here, okay? But I think we're shielded more than good enough for what we need to run the video that sneaks up and around here if we turn off the copper ports. So it's going to sneak up and around like this and go over here. Joysticks are not going to generate any real amount of noise at human speeds. I'm not that worried about that. With these pull-ups and stuff, that's not going to be interesting, and they're clear enough, in my opinion. That's not going to be a problem. So I think we're going to go with it. This has been a real quick and dirty board design. So yeah, let me know in the comments if you see any flaws. We'll start working on revision 1. Okay. So it'll end up looking a little bit like this. All right, we got another one of these buggers on the back here to jumper it onto the retro board. No parts on the back. All through hole. And we could obviously put surface mount caps on there. And that's what I would do anyway in this case, because these things cost so much money. And I've got reels and reels of tiny little bypass caps. And certainly as we go, I'll probably find things I want to tweak or change. So I won't waste expensive parts. I'll waste cheap ones. What do you think? Thanks for watching, and I'll see you next time.